A very good morning to all of you. Today we are at lecture 7 of analog electronic circuit AI system. Okay, and what is the topic today? Low frequency response of RC coupled transistor based amplifier. In previous 2 or 3 classes, we have analyzed how to get the equivalent circuitry of those transistor and why it is so called RC coupled transistor and how all the factors are affecting the gain of the transistor amplifier. Now we will be going to analyze how the frequency with respect to lower range as well as with respect to higher range, okay, how that will affect basically the transistor gain. Okay, so with respect to certain parameters involved in this network, that will mainly hamper the frequency response, that is the name of that network. In low frequency zone, we have already analyzed in the previous class how the externally connected capacitors, those are C, CD, CC, that is the biasing or coupling or you can say bypass capacitor that will basically hamper the gain in the lower range of frequencies. And in the higher range of frequencies, while we have been going through the H5 module, how all those capacitors, parasitic capacitors, internal capacitors involved with the transistor based amplifier that will hamper that can hamper the gain in the high frequency zone, and that will be discussed in the next lecture. High frequency response. Now we are moving towards the topic today, that is the low frequency response of RC coupled transistor based amplifier. Now, what are the subtopics we need to clarify? That is recapitulation of the frequency response analysis and representation of the cutoff frequency of the amplifier with respect to CS, that is the base terminal series capacitance, and representation of the cutoff frequencies involved with respect to C as well as CC we will analyze. And we have to declare what will be the overall lower cutoff frequency of that amplifier. That means the overall low frequency response of the amplifier that we have to sketch. As well as we have to analyze the lower cutoff frequency, and accordingly we can design the frequency, the oscillator amplifier for a particular genre of frequency. Okay. Now moving to the topic. So what is oscillator transistor based amplifier network? Let's see. We have here, this is a transistor NPN CMOS and having with the external biasing resistance R1 R2 voltage divider bias network, and RC is the connected terminal externally connected resistance, RA is the emitter terminal externally connected resistance. Where RL is the load resistance that will be coupled to CC because it is required DC to be sustained within this network DC voltage or current. That's why the CC that will only couple the AC towards the load. That's why we have provided here coupling capacitor CC, as well as CS is the AC coupling and DC blocking capacitor, because whatever is the voltage is coming from VCC, that will be kept restored at that base terminal, because base driving voltage will be provided to VCC, that is VB, right? So here that will be sustained within this network. There should be no DC outflow. So that's why this is the DC blocking capacitor involved over there, or AC coupling, whatever be the AC signal is coming through this source, when input, that will signal that will come through easily, that can pass through the CS with some impedance, and whereas no DC will be introduced through CS, right? That is the DC blocking and AC coupling capacitor. We know that capacitive impedance, that is basically 1 by 2 pi Fc, right? So with respect to DC, F is 0, so that's why we are getting here Xc will be equals to infinite. So with respect to DC, it is providing open circuit. With respect to AC, it will couple the signal, and that one is the topic today. Why it is coupling AC signal in AC signal, and if these are all series capacitors. Why series? Let's identify why it is series. Because this one is the base terminal and the connection with the base terminal, that is in series. Clearly mentioned. Similarly, it is the collector terminal, and obviously the capacitor CC is connected series. Then it is the emitter terminal. Obviously, with respect to the emitter terminal, this capacitor is connected in series. So it will ground basically whatever is the voltage appearing at that emitter terminal, that will be grounded through this capacitor, right? That's why it is called AC coupling capacitor. Okay, AC, sorry, bypass capacitor. So whatever be the voltage appearing over there at the input terminal, that will be grounded through this capacitor, right? Because otherwise, it will provide the negative feedback to this VDA input voltage. Okay, why VDA input voltage will be dropped down? Because what is the loop we can identify? This is the loop. So while it is the loop, so what will be VDA? VDA actually bring input voltage to the transistor amplifier directly. That is basically, we can say, applying KVL. What is it? VS minus to plus, VS plus to minus, minus VE plus to minus V, right? That is the voltage drop. So what is it? PS minus V, right? So this is the negative feedback voltage, and that's why V is decaying. So that's why if we provide here a capacitor, that will basically short that voltage towards the ground. So that's why VV will become worse, right? So to diminish the negative feedback effect, and the existence of R is very much important for the thermal stability. So that's why C is over there. So that's why this is called the bypass capacitor. And these are all series connected capacitors. Now my observation is that, so while all are the series connected capacitors, now we have to analyze with respect to AC. Now while A is for the low frequency range, we will today analyze for the low frequency value. So what is X? X is very high, very high, quite high. If X is very high and transistor may be equated as a resistive network, so it is RC series network, right? So while it is RC series network, almost all the voltage will drop down against those capacitors. With respect to CS, if we analyze, so while what we'll get, we will get almost all the voltage, that VS part that will basically drop down against CS. And whatever the VI is basically VS minus V of XCS, right? So here V of XCS is very high. So that's why VS will drop down. Ultimately, VI is coming, that is drop down. So that's why VO will appear drop down voltage. So while we are talking about the gain, voltage gain, so what is it? VO by VI, that will also drop down. So gain is decaying with respect to the frequency while there is the existence of series capacitors involved in this circuit. So what are the series capacitor? Series. What is the series another capacitor? C. What is the series other capacitor? CC. So these are three series capacitors, all are in series with respect to those terminal, and that basically will decay down the input voltage towards the resistive network, and that's why we are getting the gain for it. And we need to analyze accurately for with respect to CS, with respect to C, with respect to CC, what is the drop? Okay, very clear. And what will be the drop? So we need the frequency response analysis with, and basically for those series capacitor, we need the lower frequencies on our operation, because in case of high frequency, what is the impedance? High frequency near about the zero impedance will be offered by this capacitor, so it will be shorter in case of high frequency. But in case of low frequency, what is our observation? As AB is the highest gain, or it is called AB mid band gain, then what we get, that concept has given already to you. So that's why with respect to the frequency, while we are getting the 100% gain for this amplifier, that is our desire or requirement, but we are getting the gain in the lower frequencies only. And we have characterized a cutoff frequency or corner frequency that has already analyzed. And what is the cutoff frequency expression we got? That is 1 by 2 pi R equivalent of the network and C equivalent of the network. Okay, so actively we are analyzing the cutoff frequency with respect to CS in the low frequency zone. But in case of high frequency zone, we don't have to bother about CS, C or CC, because these are often as zero impedance, zero ohm impedance. That means these are all shorted in case of high frequency zone. So that's why high frequency zone, these capacitors analysis is not required. We can neglect that. But in case of low frequency zone, what we get here, the frequency, that is basically with respect to low frequency zone, the gain is decay term. Okay, decay term. And at a particular frequency, that is Xc, if the value is calculated 1 by 2 pi R C here, and that is a constant, nothing else. Okay, so what we get? We will get 70% gain there, 0.707, 70% gain there. Why our requirement is 100%. Okay, so 70% is the allowable. That is all in the game. That is 30% game. Okay, that is allowable. But beyond 70%, what we will get? We will not get the amplified, proper amplified output. We will get the attenuated output. So in that case, 70% gainful is allowed. So that's why the respective cutoff frequency expression we got already in the previous class, that is 1 by 2 pi R equivalent is equivalent. Now, in this class, what we find? We will find basically what will be the cutoff, what is the effect of CS, what will be the effect of C, what will be the effect of CC. That means we try to get the cutoff frequency with respect to CS, with respect to lower cutoff frequency, let us say, with respect to C and with respect to CC, lower cutoff frequency, that we can analyze. And among these three, which one will be the highest one? That will be the cutoff frequency, lower cutoff frequency of the transistor based amplifier. So that's why I am going to analyzing all those cutoff frequencies one by one with, with respect to CS, then CO, CC, and then C. Like this way. Okay. So we are on the sketch and we are moving towards the next slide. But before that, so what we have equated with respect to CS, what will be the equivalent circuit we have to know because we have to calculate the R equivalent. And then with CS, we are finding the frequency cutoff that is 1 by 2 pi Rs. So what will be R? What will be R of that network? Resistance of that network, R equivalent that we need to find. Okay. Similarly, for this case also, what will be R equivalent that we need to find as well as associated with C value. So we will find 2 pi RC by 1 by that will be the cutoff. Similarly for CCO. Let's see one by one we can progress. Now see what is the equivalent, R equivalent network. That will come from the AC equivalent circuit. So what is the AC equivalent circuit we find? The frequency at which occurs X equals to R, that will be the characteristic frequency. And what is that frequency? F1 equals to 1 by 2 pi RC. Looking from CS, so what we get? FLS is equals to 1 by 2 pi RS plus RI into CS. Now what is RI? What is RI? Okay, what is RI? RI is basically what we find here at the base terminal R1 parallel R3 in series with RS. And then we have here that is beta R, right? So what we get here R1 parallel R2, then we have beta R, right? In series with RS. So what we get here, this is the base terminal. This one is R1 R2 parallel coming because VCC will be grounded, right? Let's see. What's the network? VCC will be grounded over there. So if VCC is grounded, so if VCC is grounded, so what we get here? VCC grounded, R1 from base to ground, then R2 from base to ground. Then what we have? RS, that is through CS, it is coming from VS, right? That we have to incorporate. As well as there's the RE model of the C mode transistor, what is base interjunction that will be reflected as beta R, right? And where IB is the conservation of current. It's fine. What is the network? So what is the network we found? Here say VS in series with RS, then parallel with R1, then parallel with R2, then beta R. Okay, and where IB is the current flow. Similarly, at the output, we have beta IB because it is from the RE model that we have taken because it is input impedance that will be the transistor as a current control current source. Can you remind current control current source? Because you know that if we sketch IC versus DC graph, so what we get IC versus DC graph, we will get here after a certain value of VC, there's the constant value of current. Okay, so this is the saturated amount of current while transistor is in active mode of operation for the different level of ID. So for the different level of ID, that means there's a dependencies of ID. And if I say it is the current control source, control current control current source, why? Because it is this is the input current and this will be the output current. So what we can say, IC that is beta times of ID, right? IC, that is beta times of IV, and that is reflecting as a current control current source representation of the transistor. And what is the output impedance of that network? Input impedance we found, that is beta RA. What is the output impedance of that network? That is del DC divided by dynamic impedance, that is del IC, right? What is the value of del IC? 0. So what we found the impedance? That is infinite. So you can put the open circuit, leave it, or you can assign as infinite resistance as RA, right? So this part is from the transistor as a device representation in our module. So this is input current, this one is output current. I see having the dependencies over IV, that is beta AC times of IV. That is the representation of constant current source. And this one is the input impedance of the input junction. And this one is the output impedance. As it is the current source, so representation will be not an equivalent. That's why this is parallel to the current source. And we are getting R1 as the infinite impedance. So what we got here, this one is the RN module of the transistor part, and this one is the part is coming giving that transistor in this part. So what is this part? R1 parallel R2 to ground, because VCC has grounded, and then we have RS in series with PS, and leaving that capacitor, that capacitor is inverted. Okay. Now, in this case also CO is over there, or CC is over there, and there will be C in parallel with the RE. That will be considered, taken into consideration in the next analysis. So, what is our observation? Let's clear out this stage. What is our observation from this input loop? Let's see. What will be the total equivalent resistance? Total equivalent resistance we find here R1 parallel R2, right? R1 parallel R2. Okay. Then what we have considered here, beta I. Only leaving one, because beta is very much greater than 1. That's why we are considering R into beta plus 1 as beta I, right? Beta I. So we are getting three parallel resistances looking from this side, because CS is there. Okay, that will be given in the next slide. So let's move to the next slide and find what is why this expression. And if we want to get the equivalent resistance for RL, so we got clearly R1 parallel R2 parallel beta I. Okay, and then we need to find the lower power. Let's move to the next slide. We have really clear all these things, and we are moving to the next part. So let's see, looking from CS. So how it is looking? What is the diagram? C. This one is CS, right? And then this is RS and VS as the internal impedance 0. That's why I shorted. Then this is the base terminal having with R1 parallel R2, and this one is the resistance, that is beta R. And let us say it is simplified beta R. So what you have here, a total equivalent resistance R1 parallel R2 parallel beta R in series with RS, that is plus RS. That is there. And then we have 1 by 2 pi RC. That one is the expression of the cutoff frequency, right? So that CS involved with respect to CS we are analyzing. That's why the R equivalent is RS plus R1 parallel R2 parallel beta R, and then CS is basically the capacitance involved at that terminal. So 1 by 2 pi RS plus RI into CS, that will be the lower cutoff frequency. Okay, so we have to find what will be the expression, what is our requirement for the lower cutoff frequency, and accordingly we have to purchase what should be the, we have to suggest what will be the value of RS, what will be the value of R1, R2, like that, and we have to purchase the transistor looking into the consideration what will be its internal impedance, that will be defined in the data sheet also. So we need the help of data sheet also to calculate, to design the lower cutoff frequency. Pardon me. Let me clear the sketch. Moving towards the next one. So in this way we can calculate the cutoff frequency with respect to CS. Now how to continue and what is the effect of HCS basically. See what I said here, then as because of the presence of the capacitor, here this one is the R equivalent resistance, this one is the CS, or whatever be the capacitor involved, Vi we are providing here, Rho we are getting against the resistance. Now, as Vi decreases, then Q will also decrease, then gain will decrease, right? That one is our observation. So let's see why there is no existence consideration of the Cs, the existence of Cs. So what we found, Vi mid with respect to lower frequency, that is the higher frequency range, Vi mid frequency range. Meaning after the lower frequency range. So what we have, Vs into Ri by Ri plus Rs. That will be the total impedance. Okay. Ri plus RS means here basically we are considering that RS. Okay, that RS. And we the VS as input voltage. So what is at cutoff frequency? What we achieve at cutoff frequency 70%, 30% decay in gain. Okay, why? Because 30% decay in input voltage. So what will be the expression in that case? In that case, the expression will become Ri into Vs, that will be same parallel with divided by Ri plus Rs, and there the part of the Xc, and that is minus Jxc, impedance of the capacitor. Can you remind? J omega c, right? That is basically nothing but minus J divided by omega c. So it is nothing but minus J Xc. So you need to put it that impedance along with its phase also. Okay, as a what you can say, that is the impedance offered by the capacitor. So we got here Ri plus Rs minus Jxc as the impedance as a whole of this network. Okay, so that's why this is the representation why Pi is decaying with respect to the low frequency range of operation. And that is the cost decay view as well as the decay AV. So one can find the frequency response. While frequency response, we are talking about the gain versus frequency graph, and there is a decaying input as well as output voltage as well as uniform kilopi. And from where we can get the cutoff, right? So let me clear all this stage and we are moving. This is particularly for the numericals we are moving towards. Now, what will be the cutoff frequency with respect to CC we have to determine, because previously what we have analyzed, that is with respect to CS. Now with respect to CC we will analyze. So let's take the transistorized network as a resistive network along with this CC as a series capacitor involved in this network, and that is in series with RL. Let it fine, and then we need to Thevenin's that network. So we need the equivalent network. Okay, then we will move towards what is RO, why it is this expression, and what is the lower cutoff frequency expression. Then we can find if we get the total equivalent impedance of that resistive transistor amplifier network. Okay, leaving system. Moving to that part. So what is the output loop? Output loop is nothing but a current control current source representation with RO impedance, that is we can say that is infinite impedance, ROS infinite impedance. So one can regulate the output impedance of the transistor, that is quite mega range. So there is no current flow through that part, so that's why all current is moving throughout RC parallel RL that network. Okay, that is the physical phenomenon you can say. So RO is infinite. As it is the current source, so what will be the internal impedance? Ideally, it will be infinite. So looking from CC, we need to look from CC now because this is the loop, and CC from where we are calculating the cutoff frequency. So looking from CC, what we get? This one is RC, this one in parallel with R, right? This one in parallel with infinite again. So that's why RC parallel infinite, we are getting RC near about. Then RC plus RL, that will be the total impedance of that loop. Okay, along with CC value. So what we get here, RO is equal to RC parallel small RO, or RO will be considered as infinite. So we may consider RO is near about capital R. Now what is the total impedance of that loop? That is RO plus RO. In multiplied with CC into 2 pi, that we are getting here. The lower part of frequency with respect to CC, that is basically 1 by 2 pi RO plus RL into CC. That is the lower cut of frequency expression we are going to use for the calculation or design purpose of the network. Calculation or design purpose of the network. Okay, that will find the cut of frequency with respect to RC and RA. So what we found? RC parallel R. Okay, RC parallel R. So let me clear on my sketch and we are moving to the next part. So while we are getting, will be analyzing now the effect of C. Now the cutoff frequency we need to find with respect to C, and accordingly we design the amplifier. Okay. Now with respect to C, if we consider, so we have to move the network from CE, that part. Okay. So what we have equated in this network, let's see. VS will be shorted because it is internal impedance 0. Then RS, then we have R1 parallel R2, then we have this resistance beta RE. Okay, just this will be beta RE, neglecting part 1. And then we have capital RE resistance, okay, through which I current is flowing. And up to that part, up to, let's see, sorry, up to this part, the current flow is concerned with IB, and up to through RE, the current flow is I, right? So, what is the equivalent resistance we find? That gradually coming from there. So, R is parallel R1, that will be small r is, okay. R is parallel R1 parallel R, that is R is test, okay. Now, as it is through beta RE, so what we get? This is IB current. So, RE, sorry, R is test plus beta RE, right? R is dashed plus beta. That will be the total resistance of that encircled part, right? Now, as the current flow is IB, but we have to consider that current flow as IA because it is a single network. We will consider with a single current, and that is I. Okay, so reality is that is the flow. But if we consider I as the flow, so what is the adjustment? RS test plus beta RE multiplied with IE, we need IE is nearly equals to IC, and that is nearly equals to beta IB, right? Just put beta IB. Now, what is the extra over there from this expression? That is basically beta. So we need the beta adjustment. That's why beta will be divided. So beta will be cancelled. So ultimately the adjustment is made such that this current flow should keep sustained IB, that we are considering the current flow as IB. So adjustment is beta. Okay, beta will be divided. That's why what is the expression we are using? RS test by beta plus beta RE by beta. So that's why RE. So here RE resistance we found here are equivalent, that is RE. Now it is the current I is flowing, as well as we have considered after the adjustment, that's the current I. That's why RS test by beta plus RE in parallel with RE. That is the total equivalent resistance we found looking from C. What is the Thevenin equivalent resistance? Right? Then what is C equivalent? That is C only. So what we found here, lower cut of frequency with respect to emitter terminal capacitor, that is 1 by 2 pi RE equivalent resistance into C. So in this way, in this approach, you will find the cutoff frequency with respect to C, right? The cutoff frequency with respect to C. So what we previously found, we previously got that the expression for the cutoff frequency with respect to CC, expression for the cutoff frequency with respect to CS. So these are three cutoff frequencies we have analyzed till. Now, which one will be the highest one? That will be the cutoff frequency of the lower range of the transistor amplifier, right? So this is the expression we got finally. This one is the cutoff frequency with respect to emitter terminal capacitor. Now, what is the three cutoff frequencies that I have drawn here the graph? So frequency versus gain graph, that will fall minus 3 dB, that means 70%. Okay, that gain fall occur, that has already analyzed. Okay, The rainfall occur here at FLE, at FLC, at FLS. Now, which one will be the highest one among these three? That will be the cutoff frequency. Lower cutoff frequency of the transistor, that is the common sense. Okay. So overall, lower cutoff frequency, that will be basically here FLE according to my stage. So lower cutoff frequency with respect to emitter terminal resistance. So capacitor. So one should analyze, one should design like this way. The lower cutoff frequency should be, that's RE into C. Okay, so if we design like this way, that the lower cutoff frequency with respect to emitter terminal capacitor, and that expression we are going to use for the design purpose. Okay, so let me clear all these things and we are moving towards the next slide on numerical. There's the application. So for the same network, same circuitry, we are going to analyze what will be practically, what will be the cutoff frequency. Okay. There, these are the all practical data, and what we have here, all the data are given. CS is 10 farad, C is 20 farad, CC is 1 farad, RS is 1 kilo ohm, R1 is 40 kilo ohm, R2 is 10 kilo ohm, RE is 2 kilo ohm, RC is 4 kilo ohm, RL is 2.2 kilo ohm, given beta. Rather, it is basically beta. Beta is 100, other is infinite we need to consider, and VCC is 24. So what we perform first, what we have to analyze because we need to get RE. Now what is RE? RE is basically what thermal equivalent voltage 26 millivolt that we have already derived, divided by capital I in the previous class, and that is DCI. So how to find DCI? Let's see, very simple in the diagram what we got from the biasing network. So from the DC network you can get DCI, right? So what was that network? That network involves the voltage divider biasing circuit. That one is R1 and this one is R2. That is grounded. So what is the voltage here? That is called VD with respect to VCC. So what is the voltage? VE, that is basically VCC into R2 divided by R1 plus R2. That is basically VV. Now, after getting VV, and we have the value of VDE. What is the VDE value? That is 0.74. Now, this is the emitter terminal resistance through which the current flow is I, right? So this is RE. So what is the drop against RE? That is called V. Now what is V? What is the relation in between VV and V? That is, we can say VV equals to VV minus V. Plain and simple, that is the potential. VV minus V. So we can easily get the expression, value of V, that is VV minus VV, right? VV minus VV. VV minus VV, sorry. That is what we get, VE, that will be equals to VB minus VB. So whatever is the value of VB we have to calculate, and then minus of 0.7. Minus of 0.7, that will give the value of V. Okay. So in this way one can calculate V, and once we are getting VE, then we can calculate IE. Very simple because V is the drop against RE. So VE divided by IE. We may calculate in this way what is the value of the emitter terminal current. Okay, and that will help to calculate the emitter terminal resistance AC equivalent dynamic impedance, that is 26 millivolts divided by capital I. Let's clear all those things. Okay, then what we get here, see, from the DC analysis we have to analyze RE small I, and then we have to calculate all the cutoff frequencies, lower cutoff frequencies with respect to CS, with respect to CC, with respect to CE. Then among these two, which one will be the highest one? That will be the cutoff frequency determined for this amplifier network. Then we clear all these things and moving towards the next slide. So what we got from this network, what is VB? We have to calculate. That is drop against R2 that I have already stated to you. That's R2 into VCC divided by R1 plus R2. And what are the values if we put R1, R2, VCC? Then we found there the value of VB we got, that is 4 volt. If VB we got 4 volt, Then what is V? V is basically VB minus VB, right? What is VB for the silicon transistor? That is zero point 0.7. So what we got? That is 4 volt minus zero point 0.7, that is 3.3 volt. Now what is RE? I is drop against RE. That means V divided by RE. So 3.3 volt divided by 2 kilo ohm. So we got 1.65 milliamps. So while it is 1.65 milliamps DCI, so what is RE? Dynamic impedance at the meter terminal resistance and meter terminal of the transistor device. So 26 millivolt divided by 1.65 milliamps. So we are getting 15.76 ohm, right? Now we have to calculate suppose mid-term. It's very simple that we have already analyzed in any model. So what we got? AB mid, that will be become VO by VI, that is basically minus RC parallel RL divided by RE. If you haven't in mind, so you can very simply analyze as because RC parallel RL is the output impedance, then what will be the drop against that? That will be basically IC. IC is the output current, this is the output resistance. And with negative sign as because IB is the input current towards the device, IC that is towards the device. So IC is towards the device, so load flow is opposite, right? Negative. Load flow is, if it is downward, then it will be regarded as the positive voltage, but while load flow is towards the device, IC is towards the device, so we are considering the load voltage as negative. Okay, so that's why minus RC parallel RL into IC, that will be the output. And what is the input voltage? That is against the dynamic impedance beta RE into beta RE, that is into IB, right? Now beta into IB, that is basically IC. So IC will cancel. So we are getting here minus RC parallel RE divided by RE. So minus RC parallel RE divided by RE, that will be basically minus 90 over here if we calculate. So that is the gain. Now, we may have to use that gain in case of higher frequencies on our operation. Tone of the frequency response analysis, whenever we will do that, we will work in that case. We need that value. Okay. Now, see, after getting the value of RE, we can calculate now what will be the impedance offered by input Y. We are taking into consideration that is with respect to CS, we are analyzing the part of it, right? So what is it then? R1 parallel R2 parallel beta R, that is 1.36. Now class with RI is given RS, that is given 1 kilo ohm. So put 1 plus 1.32 kilo ohm, then 2 pi multiplied into CS value 1 divided by that, we are getting the lower cut of frequency with respect to CS, and that is 6.86 Hz. We are getting only Hz, that is 6.86 Hz. Or with respect to CS, if we analyze. Now with respect to CC, what we got? Lower cut of frequency with respect to CC, that is 1 by 2 pi RC plus RL into CC. So what are the values given? That we know. And what we got? The value ultimately 25.68 Hz. So lower cut of frequency with respect to those values, we are getting 25.68 Hz. Now, in this way, similar manner, as we establish the relation FLE, that is equal to 1 by 2 pi REC. So let's calculate RE. What you got the value? That is 24.35 ohm. And if we put that value, we are getting the cutoff frequency with respect to emitter terminal capacitor, that is 327 Hz. So these are three impedance. These are three cutoff frequencies we got. Okay, among these three, which one is the highest one? Which one is the highest one? See, FLE is the highest one. Okay, if among these three. So FL, this one is the C. So FLE is the highest one, that is 327 Hertz. 327 Hertz we got, last one. So this one will be declared as the lower cutoff frequency of that network. Okay, lower cutoff frequency of that network. So what is the step involved to calculate this kind of numericals from this kind of numericals? We have to design the lower cutoff frequency of that amplifier. Okay, while we are designing, so for this given data, we can calculate the lower cutoff frequency. What is the first step? The first step, you need to calculate RE. Okay. To calculate RE, what is the necessity? Necessity is we need to calculate VB. From where we are getting VD? We are getting VD from the C analysis or biasing network. We are getting VD. Okay, from where we can calculate actually V. Then after getting V, we can easily calculate I. So first step is to calculate RE. To calculate RE, first step is we require DC analysis from where we are getting VD, V, and then I. We need to find I. Okay. So while we are getting I, to calculate, we need to calculate RE. Okay. So we are getting RE like this way. So whenever we are getting RE, we have all those expressions. That is a lower part of frequency 1 by 2 pi RS plus RI. Here RE involved. Okay. RI in RI, yes, RE involved. Beta. So we are putting the value of beta 100. So we will get a cut of frequency with respect to CS, with respect to CC, with respect to C. Now, while we got all those things, then all those three parameters, among these three, which one is the highest one, that will be regarded as the part of frequency. Okay, so in that case, FLE, we are getting the lower part of frequency with respect to emitter terminal capacitor or bypass capacitor. So we may solve this sort of numericals as well as we can design according to our choice. What will be the lower cut? What may be the minimum amount of frequency that can pass through that network transistor based amplifier such that that can take into the part of the amplification so that we will design like this way. And accordingly, we need to purchase after designing. We need to purchase all this and uh, what you can say the discrete components, okay, and then we can design the amplifier in our own hand. So there may be the hands-on, okay. So you can try also at your home. So what we have analyzed today, we have analyzed how to get the lower part of frequency of that transistor-based amplifier, not only for the numericals, and step by step that I have shown to you how to calculate all the resistances and as well as the cut-off frequency. So while we are calculating resistances, so we are fixing the design considerations. So while taking into consideration all these designs limitations, then we can easily fix up our need, and then accordingly we can design all this on a transistor-based amplifier network such that it can provide the low frequency operation very smoothly. Okay, so that may design this analysis that may help you to design the amplifier network in the lower frequency range. As well as in the next class, we will analyze how the transistor-based amplifier gain will decay down after a range of frequencies was higher range of frequencies. In that case also, the series capacitors will not involve in, only the series capacitor will not affect only will not affect the transistor gain, but only the parasitic capacitors those are involved in this network internally that will have